In this video, I want to discuss vectors, how we add them, how we find their components. Vectors are one of the things that makes physics different than any other math or science class that you've probably taken before. So it's really important that we get a good understanding of vectors. First of all, you need to understand that a vector is a quantity, a measurement, where direction makes a difference. If direction doesn't matter, those measurements are called scalars. Scalars include time, temperature, energy, a lot of things, including speed and distance. But when direction matters, we have a vector. Displacement, velocity, acceleration, and force are just a few examples of vector quantities. There's two basic methods for adding and dealing with vectors. One is graphically. If we're going to deal with vectors graphically, we're essentially doing scale drawings. We have to draw vectors to scale. And we also have to make sure that every vector points in the correct direction or at the correct angle. That means if we're going to add vectors graphically, we're probably going to need a ruler, we're probably going to need a protractor. Truthfully, we're going to limit how much we do this. Drawing them graphically is just not the best way to get the most precise answers. But drawing a sketch graphically gives us a better indication of what we think our answer will look like. So it's good to understand it, even if it's not going to be our primary method. Basically, we add vectors graphically by connecting from the tail to the tip, or the tip to the tail, however you want to think about it. Let's suppose we have two vectors. I'm going to say this vector is 5 meters. And I want to add a second vector. I'm going to let my second vector be blue. The second vector is 8 meters. Notice when I add vectors graphically, these happen to point in the exact same direction, so that's the easiest type to add. I start my second vector at the tip here. I put the tail here, so I put the tail to this tip. The resultant vector, or the sum of those vectors, you begin at the first vector and it ends at the tip of the second. So let's look at that. My sum would begin at the tail of the first and go all the way to the tip of the second. Well, that's obviously just 13 meters. As long as vectors point in the same direction, they're no trouble at all to add. Even if they point in opposite directions, it's still really pretty easy. If my first vector is, let's say it's still 5 meters to the right, I'll use the same one I had a minute ago. But my second vector goes to the left. Remember, the tail has to start here. I'm going to draw it underneath because I don't really want to draw on top. So we started there. We went 5 meters to the right, then 8 meters to the left. The resultant vector, or the sum of those, remember, has to begin where we started. So it's going to begin right here, begins at the beginning and end right here. That's obviously 3 meters. But what's different is this time we have 3 meters to the left. Again, if they lie in the same or opposite directions, we could have done this just using a little basic algebra where we consider the right to be positive and we consider the left to be negative. So this would just become positive 5 meters, negative 8 meters equals negative 3 meters. We all agree that we consider right to be positive and left to be negative, just like we consider up to be positive and down to be negative. So when they're a straight line, vectors are not going to be a problem. We can also do it fairly easily when they're perpendicular to one another. Suppose I have something that's 4 meters to the east. And my second vector, the vector that I'd like to add to that, is 3 meters south. Okay. We could actually solve this quite easily using the Pythagorean theorem. We want to start at the beginning of the first, and our resultant goes to the end of the last. So there's our resultant. If you remember your Pythagorean theorem, d squared plus 4 squared equals r squared, this should measure 5. If we've drawn it to scale, whether we might be using centimeters, we probably couldn't actually draw something 3 meters and 4 meters, this would measure 5 meters. We could get a protractor and measure this angle. What we would find is that this angle would measure approximately 36 or 37 degrees, I believe. About 37. And we'd have to describe it. How would we describe that resultant? We'd say it's 5 meters at 37 degrees. It's not 37 degrees south. We would say south of east. It doesn't point east, it's 37 degrees south of east. Okay. All of that can be done with rulers and protractors. So far we've only talked about adding vectors graphically, but it's possible that we might need to subtract vectors. That's a little bit different, so let's take a minute and look at how we go about subtracting vectors. Let's suppose we have 2 vectors, and we're going to make it easy. We're going to keep them pretty simple. V1 is a 2 centimeter long vector that points directly to the right. V2 is also a 2 centimeter long vector, and it points directly up. If I were to add those two, it would look like this. 2 centimeters to the right, 2 centimeters straight up, and my resultant begins with the tail of that first vector to the tip of that second one. It goes from here to here. If I used my Pythagorean theorem or I measured it, I would find that that's going to be, oh, I didn't even write it down. The square root of 8 . about 2.8. Now, what would be different if we subtracted it? When we subtract vectors, we add the opposite. So we make a new vector. Negative V2 looks like this. That is the opposite vector. We often use the term an opposite vector. If we want to subtract, we will have to add the opposites. You probably learned that in algebra. When you want to subtract, add the opposite. So V1 minus V2 is equal to V1 plus the opposite of V2. So now when I add, I'm going to add this vector, V1. That was my 2 centimeter vector this way. And to that, I'm going to add this vector, negative V2, the opposite of V2. Also 2 centimeters. This time when we add, our vector points in a different direction. It's still 2.8 centimeters, but if you recall, when I added V1 plus V2, the first example, it looked like this. And the resultant was at positive 45 degrees. This time, that would be at positive 45 degrees. It's 45 degrees above horizontal. This time, this points downward at negative 45 degrees or below horizontal. So if we need to subtract, we need to add the opposite. Another type of process we can do with vectors is called scalar multiplication. Scalar multiplication just means we're going to take a vector and we're going to multiply it by some number. So for example, if I know that vector A, sometimes vectors are used capitally, is this vector, I'm going to let that vector be 2 meters long. Well, 3 times vector A is exactly what you think it should be. It points in the exact same direction. It is simply 3 times bigger. So scalar multiplication is very straightforward. It does not change the direction of your scalar, but it does change the size of your scalar. Right. All of this is helpful so that you'll be able to draw pictures, think what it should look like, but it's going to be more practical and more accurate if we use algebraic methods. So that's what we're going to look at next. Now you'll remember in physics we need a frame of reference, and we use the same frame of reference we use in mathematics. We use a coordinate system. So, or a coordinate plane. I'm going to just look at the first quadrant right now, really. But what we're doing is going to apply to vectors that are also not in the first quadrant. Let's suppose that I have a vector we'll call that vector A. Now, it's possible to get vector A by adding 2 perpendicular vectors together. In particular, if I draw this, think about this. I can think of a vector that points this direction. I call that the x component of vector A. That tells us how far vector A points in the x direction. And then perpendicular to that, I have a y component. I'm going to call that AY. Notice this vector plus this vector add together to give me vector A. Those are my components. Okay. In physics, we measure all angles counterclockwise from the positive x-axis. That's the same way you measure angles in math. So I'm going to call this angle theta. We can get the magnitude of the x and y components by some very basic right triangle trick. We know that cosine theta is equal to the adjacent over the hypotenuse. You learned that when you took trig the first time. Cosine theta is adjacent over hypotenuse. In this diagram of this right triangle, we see that cosine theta is the x component over the magnitude of A. There's different ways that people will indicate the magnitude. I don't really care about the direction of A here. I care about how big A is. Sometimes you'll see it done with absolute values. That means the size or the magnitude of vector A. I'm not going to write that, which means if I solve for AX, I find out that the X component is equal to A cosine theta. It's a really important idea. AX is equal to A times cosine theta. If we use a sine trig function, we know sine theta is equal to the opposite over the hypotenuse. Or in this case, sine theta. Remember, here's our angle. Opposite the angle is the y component, AY, over A. If I solve for AY, I get that AY equals A sine theta. Really important. We can take any vector pointing in any direction and we can get its components. Notice that it's going to work perfectly if this angle is more than 90 degrees, say we do 105 degrees, cosine theta will be a negative value and we will get a negative x component. It will tell us that the vector is pointing to the left and not to the right. Same thing here. If we have a value where the angle is down below the axis, sine theta will give us a negative value, and we'll know that the y component points down. So even though I drew this in the first quadrant, this works perfectly regardless of which direction the vector is pointing. Vector components can be positive or negative. If the x component's positive, it's pointing to this direction. If the x component's negative, it's pointing in a negative x direction. If the y component is positive, it's pointing up. If the y component is negative, we know it's pointing down. Okay. Now, looking at these pictures, we also get this very important relationship, and that's the Pythagorean theorem. We know ax squared plus ay squared is equal to the magnitude of a squared. A squared plus b squared equals c squared. That's just the Pythagorean theorem. Also, a very important relationship that relates x and y components to the magnitude of the vector. Anytime you have two perpendicular vectors, you can put them together. You can add them using Pythagorean theorem. All right, there's one more really important relationship I want to point out. I'm going to move this out of my way. Put this down here. And we haven't talked about what information tangent theta gives us. Tangent theta is opposite over hypotenuse. So if I'm here, tangent theta is AY over AX. Now, we use this relationship anytime we need to find the value of theta. If we know the y components and we know the x components, we can find the value of theta. Theta is equal to the tangent inverse of y over x. Now, there is a problem. It's an important problem too. Inverse tangent is only defined for quadrants 1 and quadrants 4. And there's a very good reason. If AY and AX are both positive, we're in quadrant 1. If AX and AY are both negative, we're in quadrant 3. But your calculator cannot tell the difference because two negatives are going to make this positive. So regardless of whether you're in tangent in quadrant 1 or whether your angle points in quadrant 3, you're going to get the same answer here. And it's not going to be correct for both of them. What do we have to do to take care of this? This is correct for quadrant 1 and quadrant 4. How do you know which quadrant you're in? You look at the values. If AX is positive and AY is positive, you know you're in quadrant 1. If X is negative but Y is positive, you know you're in quadrant 2. If they're both negative, you know you're in quadrant 3. And finally, if X is positive and Y is negative, you know you're in quadrant 4. So another way of thinking about this is that this formula is correct anytime X is positive. Quadrant 1, quadrant 4. Theta is going to equal the tangent inverse of AY over AX plus 180 degrees if you are in quadrant 2 or quadrant 3. So this is really easy. Finding components is really easy. Adding perpendicular vectors is really easy. If you know the components, just pay attention to the sign and you'll be able to figure out the angle. Right. So we've got a lot of important formulas here. All of these are on the formula chart for your course, but it's stuff we really need to be comfortable with. All right, so how are we going to add vectors now that we have a lot of information? I'm going to give you a step by step. Now, you can have as many vectors as you want. I'll write it as if we're adding 3. But we're trying to find some resultant vector that equals to vector A plus vector B plus vector C. Notice when we write vectors, we put a little arrow that indicates it's a vector measurement. The first thing we're going to need is to find all of the X and Y components. How are we going to do that? actually, I'm going to keep it a little simple. To get the x component of the resultant, how far does this point in the x direction? We simply add up all of these x components. Ax plus bx plus cx. And there could be more, but I'm going to stop there. How do you get x components? This is going to be a cosine theta plus b cosine theta plus c cosine theta. Now, really important, we're measuring that angle counterclockwise from the positive x-axis. But as long as we're measuring it counterclockwise from the positive x-axis, this works. To get the y component of the resultant, we simply add up the y component of each vector. Ay plus by plus cy. That's going to equal a sine theta plus b sine theta plus c sine theta. So now we know the value of Rx and Ry. We need to get the magnitude of R. We're going to use the Pythagorean theorem. R is going to be equal to the square root of Rx squared plus Ry squared. That's what our Pythagorean theorem has always looked like. Rx squared plus Ry squared equals R squared, but we just need R. And finally, we need that angle. Theta is equal to the tangent inverse of the y component over the x component. If the y component is negative, we need to add 180. And I said that exactly wrong. If the x component is negative, we have to add 180. That'll put us in the second or third quadrant. At 180 degrees, if Rx is negative. That means you're in Q2 or possibly Q3. So that's our steps. It's a simple 4-step process. So let's do an example. We'll do a simple example. We'll do a harder example. We've been adding mostly displacement vectors or just, things that look like distances with meters. Let's just do one for velocity just to be different. Possibly you might have a velocity vector of, we'll let this be a bird. And the bird is flying 35 meters per second. At 75 degrees north of east. That's the velocity of the bird. We'll call that vector A. I'm going to call it vector B. B for bird. So the bird is flying 35 meters per second at 75 degrees north of east. We'll see what that looks like in a second. And the wind, which I'm going to call vector W, is 20 meters per second. West. We're going to draw a picture just to have a feel for what this should look like. and then we're going to work the problem. So here's my coordinate plane. And the bird is going 75 degrees north of east. Well, this is east, this is north, 75 degrees north of east. That just means it's flying at 75 degrees. So there's 75 degrees. And we know the bird is going 35 meters per second. Okay. What's the wind doing? The wind is blowing, it's not as big, it's only 20. This is blowing straight west. This is going to be kind of iffy because I'm not really sure if it's going to be in quadrant 1 or quadrant 2 yet. But that's okay. This is just a sketch. So if I start at the beginning, I think the resultant looks like this. There's the bird, 35 meters per second at 75 degrees. And there's the wind, which is blowing 20 meters per second to the west. Let's think about the angles here for just a minute. 35 degrees, that is 70 degrees, but what's the angle for flying to the west? Well, for flying to the west, that another way of saying that is he's flying at 180 degrees. Remember, east is 0 degrees, north straight up would be 90, to the west would be 180 degrees, and straight down would be 270 degrees. So we've got our vectors. Our x component is going to be 35 cosine 75 plus 20. Let's assume that we have at least 2 significant digits. So I'll put 20.0. And we have 20 cosine 180. Now, just want to show you what happens. I'm going to kind of do this slowly in steps so you can see. If I do 35 cosine 75, it's trying to give me exact answers instead of, this is the one I need. Check my mode. Let's make sure I'm in degree mode. I am. So 35 cosine 75 comes to be 9.059. Now notice I'm carrying extra places because I'm going to round to 2 digits, but not till the end. That seems okay because it's going mostly up. It's not going very far out. If I do 20 cosine 180, I get negative 20. Well, that makes perfect sense because the wind is pointing in the negative direction. So what I end up seeing is that my x component is about negative 10.941. So I'm definitely going to be in quadrant 2. The x component's definitely going to be negative. Let's kind of circle that. That's a box that in. We're going to need that. Now I got to get the y component. The y component, 35 sine 75 plus 20 sine 180. Well, 35 sine 75 is 33.807. That makes sense. This vector points mostly up, so it has a large y component and a small x component. If I do 20 sine 180, I get 0, and that makes perfect sense also. The wind does not have a component in the y direction. It's pointing to the west. It's pointing in the negative x. It doesn't have any y component at all. So our y is this number. were practically there. All I have to do to add those together, and I'm just going to erase some of this, is I have to do the Pythagorean theorem. The magnitude of the vector is going to be the square root of negative 10.941 squared plus 33.807 squared. 10.941 squared plus 33.807 squared. And then I have to take a square root. And it comes out to be that R is equal to 35.53, or about 36 meters per second. Notice it's actually the bird's going a little bit faster because of the way the wind is blowing him. I didn't draw it perfectly. This vector should be a little farther that direction. What direction is that? Well, theta is the tangent inverse of the y component, the y component, 33.807, over the x component, negative 10.941. I know I'm in quadrant 2. X is negative, y is positive. Anytime x is negative, I'm going to have to add 180 degrees to that. So what does that give me? Tangent inverse 33.807 divided by negative 10.941 is negative 72 degrees plus 180 degrees. Comes out to be 108 degrees. That makes perfect sense. We know it's over 90. 108 looks really, really reasonable. Okay? The picture helps us see that the answer that we get is reasonable. Now, how do we write our answer? We typically write it something like this. We got 36 meters per second at an angle of 108 degrees. Now, if we needed to describe that better, because this is a problem where I use terms like north and south and east and west, I can figure out how to describe it a different way. If this is 108 degrees, that's 72 degrees. I could say 36 meters per second at 72 degrees north of west. But I'm not going to do that very often in this course. I'm probably going to just write it just like this. We all know we measure our angles from the positive x-axis. Okay, let's do one more. We'll make it a little more challenging, although there were some challenges in that one. In this example, we have a plane trip with 3 legs. First one, we call D1, was 620 kilometers due east. or 0 degrees. The second leg of the trip was 440 kilometers, and it was southeast or negative 45 degrees. And the third leg was 550 kilometers, and it was 53 degrees south of west. We're going to have to figure out what 53 degrees south of west means if we're measuring from the x-axis. So let's just make a little sketch. Here's west. I'm 53 degrees south. That means this angle is 53 degrees. Oh, well, if I'm measuring from east, I know all the way to here is 180. 180 plus 53 is going to be 233 degrees. Helps to get all the angles measured the same way. Okay. I didn't do this here for south of east, but I could have. Here's east. If you're true southeast, you're going right down the middle, 45 degrees. That's a negative 45. It's perfectly okay to use negative angles. We could also call that, if we wanted to go this way, positive 315. So I'll even write that. Or positive 315 degrees. Negative 45, positive 315, doesn't matter. It's going to work exactly the same. All right. I like to draw a little picture just to kind of know what I think it might look like. May not get this just right. We're going to start here, and I'm going to go due east. I'm going to let that be 620. And then I'm going to go southeast. That's straight down negative 45 for 440, so not quite as long, something like this. There's our 620. There's our 440. And then finally, I'm going to go southwest 53. Southwest is going to look kind of like this. Now, those may not be right. I went east, southeast. It's certainly not drawn to scale, but it at least gives me an idea of what I think the resultant might look like. Something like that. I think I'm going to end up going slightly to the east and south. It's going to be something like that. All right, what do we have to do? We have to get x and y components. We have to add up all the x components. We have to add up all the y components. So, our x, 620 cosine 0, 440 cosine negative 45, 550 cosine 233. Once I do that, I'm going to put all that in my calculator. This is going to be 620. It's exactly what I expect because it's going in the positive x direction. This is going to be positive 311.13. Also what I expect, I can tell that the 440 is in the positive x direction. But this one, 550 cosine 233, comes out to be a negative 331. So when I add all of that up, I get a component, an x component that I'm going to write up here because I'm going to use it again, of 600.13 kilometers. Now I need the y components. All you do to change the y components is you change all those cosines to sines. So the y component is 620 sine of 0. 440 sine of negative 45, 550 sine of 223. Sine is going to give us our y components. Well, no surprise, sine 0 is 0. This vector doesn't point in the y direction at all. I think this one points down, so I expect a negative number. Comes out to be negative 311.13. I think this one points down. Turns out that this is negative 439.25. So when I add all of that up, I end up getting a y component, negative 750.38 kilometers. So I've got those three vectors. I've added up all the x components, got that. I added up all of their y components, I got this. Okay, let's think about what this means. The x component's positive, the y component's negative, so I expect to be in quadrant 4. Well, that's what I expected here. Okay. To get that value, I use Pythagorean theorem. 600.13 kilometers squared, negative 750.38 kilometers squared, and then I have to take the square root, and I get a vector sum. And at this point, I'm going to round to 2 digits. Notice I had 2 digits, 2 digits, 2 digits. Comes out to be 960 kilometers. I don't have my angle yet. Theta is equal to the tangent inverse of y, negative 750.38 over x, 600.13. And it comes out to be negative 51 degrees. Now, I didn't add 180 because anytime x is positive, I don't need to add 180. I'm in quadrant 1 or quadrant 4. In this case, I'm in quadrant 4. If I wanted to say this with compass directions, this is 51 degrees south of east. It's below the x-axis instead of above. If I want to add 315, I can write it as measured the other way. Okay? Not too bad once you really understand how to do it. There's one more thing I want to kind of do with this problem. I'm going to leave these measurements up here, all of this. No, I'm not. But I may write them down again. Let's go on. I want to talk about one more thing. And that's unit vectors. That purple pen is about decided it's done. If you're taking 1401, we probably will not be using unit vectors. If you're taking 2425, we definitely will be using unit vectors from time to time. Unit vectors have a length of exactly 1 unit. And they're used to define vectors that point along the coordinate axis. we want to be 3D, so here's Y, here's X, and you have to use your imagination and picture the Z-axis that points out of the board, straight out at you. So we have X, Y, Z. The unit vector that points along the X-axis, I think I'll change colors for this. Is called I, and the book uses a little housetop on it. Some might use a little arrow on it. The unit vector along the y-axis is J, and the unit vector along the z-axis is K. So I, J, and K. I, that means it points in the direction of the x-axis. J means the vector points along the y-axis. And Z means the vector points along, not Z, sorry, K points along the z-axis. These are basically just vector components. What vector does the vector have in the x direction? What's the component in the y direction? What's the component in the z direction? So if we look at our previous example, and we want to think about it a little bit, when we had the first vector was 620 kilometers at 0 degrees. Another way we could have written that is to say that D1 was 620 I. It pointed in the I direction. Now, for the second vector, I'm going to erase this now. See what, I'm going to erase all of this and just kind of rewrite. So we know we have unit vectors. They point along X, Y, and Z. If we look back to our previous example, the first leg of our journey was 620 at an angle of 0 degrees. That can be written as 620 I, because 0 degrees is along the positive x-axis. When we did the second one, D2, it was 440, but it was at an angle of negative 45 degrees. When we did the x and y components, the x component, 440 cosine negative 40, let's do that. 440 cosine negative 45. It had a y component, an x component of 311. When we did 440 sine of 45, sine of negative 45, it's very important. It had a y component of negative 311. So that's a J. X component, y component. The third vector was 550, and it was at an angle of 233. If I write this using unit vectors, 550 cosine 223 was negative 402 in the I direction. 550 sine 223 was negative 36. Whoa, I got a mistake here. 233. I typed in 223. Let's go back. Cosine 550 cosine 233 was negative 330. That's what we had before. 331. We'll round it to be accurate here. 550 sine of 233 was negative 439J. So basically, we're using our unit vectors to say this vector pointed this much in the x direction, this vector pointed this much in the x direction, this much in the y direction. To get a resultant in using unit vectors, sometimes these are called in rectangular forms, really easy. We add that up. If we add this up, we end up getting 600I minus 750J. You'll recall that was our Rx, this was our Ry in the previous example. So unit vectors are just vectors that have a length of 1 that indicate whether a vector points along the x, y, or z axis. And then we use the symbols I, J, and K for those. Okay, you'll see lots more examples with vectors as we work through the course together, but I hope this gives you a good, solid foundation in vectors.